Question 30 from the reading. What is the pH of a solution after the addition of 5 milliliters of 0.01 molar HCl to a 25 milliliter solution of a buffer that contains 0.1 molar potassium fluoride and 0.2 molar hydrogen fluoride? This is actually a challenging question, so we have to do a few different calculations and basically move everything over into moles. Once everything's moved over into moles, it'll be easier to see our changes in moles after we add this strong acid to our buffer. And then after we do that, then we can find our final concentrations and our final pH of this solution using the Henderson-Hasselbalch equation. All right, so the first step, I want to break everything down into moles. So I have my HCl. I have 5 milliliters of a 0.01 molar solution, right? Molarity is moles per liter. And I have, of this HCl solution, and we'll just call it H plus because essentially we're adding a strong acid. Of this solution, right, I have a 0.005 liter solution. Do the same calculation with fluoride, right? And that's from my potassium fluoride. That's my source of fluoride. So for that, I have a 0.1 mole per liter solution. And of that solution, I have 0.025 liters. And of my hydrogen fluoride, right, I have 0.2 moles per liter, and I have the same 25 milliliters of that solution. Take a look, right? Liters cancel out when I multiply, and I'm left with moles. So I'm going to have approximately 5 e to the negative 5 moles of a proton, 2.5 e to the negative 3 moles of fluoride, and 5 e to the negative 3 moles of HF. So there's the moles of all of those. Now I need to figure out where does this strong acid react? What does this strong acid react with? And we can set up our little chart to show our relative concentrations, right? Our relative amounts. And so here's HF, right? And here's my fluoride. My HF, right, is 5 e to the negative 3 moles, and this is 2.5 e to the negative 3 moles. I add a strong acid to that. And what is the strong acid going to react with? The strong acid is going to react with the conjugate base of HF. So fluoride is going to react with that acid to form more HF. So we should expect to see the concentration of HF go up and the concentration of fluoride to go down. By how much? Right? By 0.0005 moles, because that's how much of a strong acid I'm adding to this solution. So I'm going to react with the fluoride, so I'm going to subtract from that concentration. And the product of that reaction is more HF, so I'm going to add to that concentration to get my new concentrations after equilibrium. More importantly, all of the strong acid reacts, so there's none of that left after I add it to solution. It reacts completely. So I'm going to subtract. I get 2.45 e to the negative 3 molar fluoride, and I get 5.05 e to the negative 3 molar HF. Before I can do the Henderson-Hasselbalch calculation, I need to put this back into concentration. So I have 2.45 e to the negative 3 moles of fluoride, and that is in now 0.03 liters. I add together the 5 milliliters of the acid is added to the 25 milliliters of the buffer, so my new volume is 0.03 liters for 30 milliliters. Do the same calculation over here with my HF, 0.05 e to the negative 3 moles of HF times 0.03 liters to get my new concentration. My new concentrations for both of those, I get approximately 8.17 e to the negative 2 molar fluoride and 1.68 e to the negative 1 molar HF. Right, because we were adding a volume and we knew how many moles were in that, the concentration of that volume, we had to find out how many moles so that we could find what's the change in moles when I add that strong acid to this solution. The strong acid reacts with a conjugate base, fluoride, protonating that, forming more HF. Now I can do my Henderson-Hasselbalch equation. The Henderson-Hasselbalch, right, pH equals pKa plus the log of my base over the concentration of my acid. The pH of this solution equals the pKa, which is the negative log of my Ka, so the negative log of 7.2 e to the negative 4, plus the log of my base, the concentration of my base, 8.12 e to the negative 2, over the concentration of my acid, 1.68 e to the negative 1. All right, I'm going to get a pH of approximately 2.83. And again, this was an involved calculation because we had to go from volume to how many moles were there to figure out how many moles were going to react. We couldn't just go based on concentration because our volume changed. As our volume changed, so does our concentration.